Last class, we stopped here, with this problem. We'll start with this problem in today's class. Okay. So the problem is a version which I don't think you have solved. You might have solved in your bachelor's or or before that. So this is like coupled. This is coupled differential equations. So you can see dy by dx equals to x plus z, and dz by dx equals to y minus x. So you can concentrate on this question. Okay. So the idea is simple. The idea is like how we can solve. What should be your aim? Your aim should be to solve y and z. Okay, y and z. So initial condition is being given to you at x equal to 0. This is x equal to 0. At x equal to 0, the value of y is 1. At x equal to 0, the value of z is minus 1. Okay. And the step size for this numerical method you have taken to be 0.1. Fine. Now the question is, if given this differential equation, how can you find the value of y and z? How can you find the value of y and z? Because you know y is depending on x, z is also depending on x, but y depends on both x and z. Z is also depending on both x and y. So therefore, these are coupled equations, coupled differential equations. Now you know that if I gave only this, dy by dx equals to some x square plus y square plus x. If I give this differential equation to you, then yes, you know how to solve it using Ranji-Kutta method or Euler method. But if I give you this coupled system of differential equations, will you be able to solve? That's my question. Okay. Technically, the answer is yes. You can use the RK4 method and RK2 method. RK2 method I have not covered in class because it's a bit less efficient than RK4. We'll focus on RK4 only. So how to use RK4 method to solve this? How to compute the solution of this ODE? Okay, coupled ODE. That is our aim. So therefore, before that, let us see the general solution for this. So if you have, suppose any general differential equation of this form, like I'm writing just two, you can generalize into more than two. Okay? So suppose you have this differential equation dy1 by dx, that means y1 is depending on x, as how it gives us the rule, how y1 varies as x1 varies. Okay, that is the rule. That is, suppose some function f1 x y1 y2. Okay, then there is another variable dy2 depending on x, which has another function f which depends on x y1 y2. Okay, you have the initial condition for each of these equations. For the first one, y1 at x equals to x0, you have y10. Okay, and say for this variable y2 at x equal to x0, you have y20. You have to follow the notation how I am writing here. Okay. Yes. So the idea is like how we can use RK4 method to solve this. Okay. So you can easily solve this, but if you understand the notation behind this. So last time, can you tell me how RK4 method evolved? So in RK4 method, you predicted the next value of y by taking the average h by 6, k1 plus 2k2 plus 2k3 plus k4. Yes. Why you took only k1, k2, k3, k4? Because there were only one equation involved, dy by dx equal to something. Now, since there are two equations involved, you will have another set of that, another copy of those ki's, that is li's. Okay, you can take li's. Okay, so that we will see today. Yeah. So how to solve this? So we'll directly come like extension of RK4 method. Extension of RK4 method to solve this is, you know, so what you want to find? What you want to find? But there are two y's. Yes, y1 n plus 1. And also we need y2 n plus 1. then we are done. Notice that we don't find anything related to x because y1 and y2 are varying with x. X is the independent variable. X is the independent variable. Y1 and y2 are the dependent variables. Okay. So therefore, y1 n plus 1 and y2 n plus 1. So similarly, as in RK4 method, y1 n plus 1 is given by, y1 n plus 1 will depend on the previous value of y1. In almost every numerical method, you have this. The future depends on the past. Plus, you can see it is h by 6. Shall I write h by 6? Okay, maybe, yeah. So h by 6 then. What do you think? What do you guess? Okay, this will be tricky, but let me write first. Then you can match your notation with it. Okay. So some k1 plus 2 times something new, that is s1, plus 2 times something new than the other one, that is l1, plus something new again p1. Okay, we'll see what each of them are. Similarly, y2n plus 1, you can write it as y2n plus h over 6. Now, instead of k1, there will be another copy. Instead of k1, there will be a copy of k1, that is k2. Okay. Instead of s1, there will be a copy of s1, that is s2. Similarly, what should be next? Yes, then? Yes. So, k1, k2, s1, s2, l1, l2, p1, p2 almost behave like similar as per the original RK4 method. But since you have one more variable into your equation, you need eight unknowns like this. Okay, one for each. So these K1, S1, L1, P1 will go with Y1. This K2, S2, L2, P2 will go with Y2. Okay. So we'll see how these are. But before that, we need to see what are these KIs, SIs, LIs, and PIs. Okay. So what are these? What is K1 from your RK4 method? Hmm? H into, yeah. So here you have you don't have F. Here you don't have F. Rather you have F1, F2. So based on F1 there will be one K1. Based on F2 there will be a K2. Okay, you got the idea. You got the idea. So here K1 will be H times F1 of uh and yes, these are previous values, past values. Okay, does it depend on anything else? It cannot depend on anything else, right? These are the only variables remaining. Okay, what is K2? K2 will be a copy of this. Just a copy of this. It is just RK4 method. If you understand the pattern, you can easily write this. You just have to understand the pattern. K2 is, I told you, K1 is HF1 dealing with the first function. Then K2 is a copy of K1. So it should deal with the second function. So what should be K2? Yes, H into F2 of xn like the previous value. Similarly, y1n, the past value of y1. Similarly, the past value of y2. Agree? Fine. Can you tell me what is S1 now from your previous RK4 method? H into F1 of H by 2. Then y plus K1 by 2. Y plus K1 by 2. Yes. Now there are two values of y. There you could easily write y. But now you have two values of y, isn't it? Y1 and y2. Y1 and y2. So based on that, there will be two copies. Based on that, there will be two copies, right? S1 and S2. Are you able to understand? Yes. So here, what should I write? Yes, y1n plus k1 by 2, then y2n plus, no, I told you, k1, s1, sorry, l1, p1. These are friends. These are friends of y1. k2, s2, l2, p2. These are friends of y2. So therefore, if you are writing y1n plus k1 by 2, then for y2n, what should you write? Yes. So you have to just understand the pattern. Rest follows. Rest follows. Okay. Similarly, what happened? So you should quickly tell me. You should quickly tell me the values what you have wrote. D1 dy1 by dx equals to f1 dy2 by dx equals to, yes. So I wrote the solution y1 n plus 1 equals to y1 n plus is y2 n plus h by 6 k2 plus 2s2 plus 2l2 plus p2, where k1 equals to h f1 of x1n xn, sorry, plus y1n comma y2n. k2 equals to h times f2 of, similar to rk4. And then I told you l1 equals to, sorry, s1 equals to f1 of k1 by 2 plus comma, yes. Then s2 f2 of, yes, y2n plus k2 by 2. Yes, I told you these guys are for y1, that means f1 also. These guys are for y2, that means f2 also. Okay, I hope you got the formula for this. Okay, then what is L1? What is L1? H into F1 of xn plus h by 2 y1 plus, yes, s1 by 2 comma, yes. So many of them already got the pattern behind this. Next one, L2 h into, yes, just the pattern, follow the pattern. L1, L2. Then we left with only 2, that is P1. What should be P1? H into F1 of, good. So many of them are following the pattern. You just have to follow the pattern. Similarly, P2 equal to H into F2 of xn plus h, comma, y1n plus L1, y2n plus L2. Okay. I hope you got this idea. But since we multiplied all with h, then we don't need h here. Okay. We don't need h here. We all multiplied h in all these constants. In all these constants, we multiplied h. We don't need h here. Check your RK4 method. So just 1 by 6. If we don't keep h here, we can keep the h there. Got the idea? It is just common multiplication, nothing else. So got the idea. Now we have to apply this to solve that coupled ODE. Okay. So yeah, can you try to solve this? Can you try to solve that ODE, coupled ODE? So this is the question. dy by dx is x plus z, dz by dx is y minus x. Initial condition for y is given as 1. Initial condition for z is given as -1. Step size is 0.1. Okay. Now the question is, can you, so you can understand that this is f1, this is f2, right? Now how you can use them to find the solution, that is y and z? Nothing, like step size 1, I want the value of y 0.1 is how much, z 0.1 is how much. That is what numerical method does. From the given initial condition, it finds out the next value of y and z. Okay, this is the step size 0.1. Can you find based on the formula we just wrote? So this is using RK2 formula, which we are not using. We have to just use RK4. We have to just use RK4. So given the question, you already know f1 is x plus z, f2 is y minus x. Okay. Now find k1 and k2. Find k1 and k2. So now that you solved this bit complicated problem, which involved 8 unknowns actually, okay. So if it comes, you won't be asked to do a lot of iterations, rather one iteration only, okay. So you came to know that y of 0 was given to you, z of 0 was given to you, and based on this, it was asked what is y of 0.1, z of 0.1. Yes, that was the idea. So we used RK4 method to solve it, an extended RK4. Extended RK4 to solve this problem. Okay. Now the idea is like this is manually intensive. This is manually intensive. We have to carefully do the calculations and also a lot of steps. Okay. So the idea is now like can you use computational methods to solve this? Okay. So therefore, motivated by this, we will see in Python like how to solve this, mostly from an ecological perspective. Like if you go to last semester, there was one student or two students from ecology joined this course. Okay, so they attended this course because they know that in their field also they need this numerical methods to solve. Okay, how? So if you know population dynamics, so population dynamics, that is, this is really important to understand because take the example like there is humans, there are lions, there are tigers, okay, there are deer. Anyone else? Fish. Anyone? Okay. Anyone? Okay. Okay. Fine. Now there are so many creatures. Okay. So there are so many creatures like who coexist in this environment with us. Like you can see, it is never that one of them has gone extinct, but when they go extinct, it represents imbalance in the ecosystem. Okay, so you can see that lions and tigers, they can attack deers, they can attack cows, they can attack maybe, I don't think camel they can attack. Okay, so they can attack dogs, they can attack cats and all these things. Okay, they can attack humans also. Okay, so you can see through this, the population of humans and population of all those guys can reduce. Okay, but it doesn't reduce. They maintain an equilibrium such that they vary dynamically. They vary dynamically. The population of camels, the population of humans, population of tigers, population of fish, and all those things, they don't stay constant and they don't go extinct also. They vary dynamically. Like today, you might have counted a number of lions. It might be 2,500. After a week, you might count, they might go to 2,400. Next week, you can count, they might go to 2,600, like that. Okay. So we don't know. They vary dynamically. They vary dynamically in such a way that the ecosystem is maintained. Okay. Now, to how to understand this, you know the data, you get the data. Okay, how you get the data? Like they tag the animals. Okay. Similarly, how they tag us? They come, knock our door, ask how many members in the family are there, who are you, names and all. Like that, they count how many females, how many males, and they get a population census. Yes. So the idea is like now how can you model this population dynamics? That is very important in the field of ecology. Okay. So there are many models. So ecologists develop models. Okay. So some of them are like these models, Forest model, then this Lotka Volterra. Okay. If you there are many friends of yours in ecology, you can ask them. They must have learned all these models. Okay. So Forest model, Lotka Volterra models. Now the idea is, the good thing about this is, can you see that suppose Y represents the population of humans? Y represents the population of humans. Now dy by dt, the rate of change of population of humans, is a function, and it depends on how many tigers came to you. Okay. How many lions came to you? Okay. Anything else? Yeah, that much. Okay. So you can see that. Now suppose, can you tell fish? Suppose Z is fish. Now dz by dt is equals to how many humans have like trapped them. Okay. Anything else? How many like sharks have eaten them? Okay. Can you see that this is a coupled system? Like the rate of change of humans depends on tiger, lions. Okay. Now the rate of change of fish also depends on humans. So they depend upon each other. That means they are coupled. So this is the motivation why we came out of the simple ordinary differential equation to understand about coupled ordinary differential equations. Okay. So therefore, coupled differential equations are mostly everywhere. Okay. I will give you one more example. I think some of the project students are working on it. Capstone project students, some are working on it. So I will tell you that example also, but we'll move to Python for now. So, okay. Yes. So last class we stopped here. So you can see this is something known as Forest model. Okay. Yeah, the model goes like this. Like you have rate of change of population of some species X with respect to time is given by the population factor. This is a reproduction factor times X times 1 minus X by P. So this is some parameter, population parameter. This is carrying capacity. Okay, this is carrying capacity. Now the idea is, this is how the population varies. Okay, you can see that this is a good population model. Why? Because you can see the population, the rate of change of population depends on the population itself. How many people are there, it should depend on that. The future should depend on the past. At the same time, it also decreases. 1 minus x by p. 1 minus x. That means if your population, this is like normalization. X by p. This is like normalization. Okay. So the idea is 1 minus x by p is like if your population x increases, 1 minus x by p will decrease. Why 1 minus x by p will decrease. Okay. So if your population decreases, 1 minus x by p will increase. Okay. So this model, this 1 minus that quantity is there for that purpose. Okay. Now the problem is like it just tells you about one population, dx by dt. It doesn't capture that humans, suppose this is humans, this can be eaten by tiger, this can be eaten by lion also. It doesn't capture. It just tells what is the population of humans depending on the population of humans. Okay, you know, humans can also attack humans. Okay, so therefore this case only deals with, okay, but it doesn't deal with how human population is getting affected by tiger or lion. Multiple species is not there in this model. That is the demerit. Okay, so okay, but you can solve this. You can solve this exactly. Actually, it is very easy to solve. How you will solve? If you want to solve this analytically, you might have known dx by, you can bring this guy, x into 1 minus x by p equal to a dt. Okay, and you can integrate this. You can apply the partial sums rule, right? You remember this, I think. If you want to solve analytically, what is the idea? You can take this guy, integral, you can take this guy, 1 by x into 1 minus x by p as sum a by x plus b by 1 minus x by p. You have to find what are a and b's, and you can just integrate. So what will it be? Integral of this dx, x into 1 minus x by p dx is equal to nothing but integral a by x dx plus b by 1 minus x by p dx. These guys will take the form of log. I hope you remember this. Okay. So I mean to say that don't need to worry about all these things, but I meant to say that this can be solved analytically. Okay, this can be solved analytically, and therefore I have done something known as x exact in this below. You can see if you solve this, you will get this answer. Okay, fine. X exact. Okay, now suppose we don't want to solve it exactly, we want to use numerical methods. You can use RK4 method. Okay, so I have used RK4 method. K1, K2, K3, K4 I have computed. You can check these KIs. Okay, I hope these are correct. Fine. So then you have to just use this guy. Xi is that formula divided by 6. And Ti plus 1 is, Ti equals to Ti minus 1 plus H. Step size, it will increase. And those Ti values, you have to compute what is X. Okay. Now we are plotting the exact solution in cyan color and the numerical method solution using RK4 using black color. Okay. Let us see. So X represents the population in thousands actually. Okay, X is a dimensionless quantity. X is a dimensionless quantity. If you get X equals to 1.5, what does it mean? How many people are there? 1.5 into 1000. Okay, that is how much? 1.5 into 1000. Yes, that many are there. So that should be your interpretation. And at the same time, X cannot go negative. Can X go negative if X is population? No, it can go at most 0. Okay, so therefore we'll see this. You can see that it never went downhill of 0, never went negative. Okay, and this is the solution. Like you can see, time is in years. Okay, fine. And population is in thousands. You can see the black and cyan line. The RK4 method you have computed matches exactly with your analytical solution if you solve like this. So therefore you are confident that RK4 method will not give you any error. Okay, that's the idea. Fine. Now, as I told you that there are some limitations of this method, of this Worrest model. As I told you that it doesn't take care of the other populations. Scientists Lotka and Volterra modified that model to make it more even efficient, and they came to Lotka-Volterra model. Okay, so how Lotka-Volterra model looks like? So it looks like this: dx by dt equals to yes, ax minus bxy, okay, and dy by dt equals to c minus cy plus Rxy. So this is the model. You can see that you want to understand. You want to understand, like, suppose the dynamics of like um, uh, what do you call that? Usually it comes like you cannot eat eggs, like that infection comes. Hen gets infected. I forgot that thing. So how it gets infected? Okay. So suppose that this is the dynamics of hen. Okay. Hmm? You tell. Tell. You want to eat egg. Okay. So this is the hen. Okay. And this is that virus. Okay. This is the virus. Okay. Oh, what is this? You have to model like this. Even COVID, even coronavirus, when it got spread, people were not having the data. Who will go and collect the data? Everyone is at their homes. Who will go and collect the data? You tell. During the spread of coronavirus, when it started, how you get the data? It was very, very hard to get the data, that too from medicals, because the people will be coming in, they will be checking. How you will get the data? Only the medical staff will give you the data. Is that accurate data? So at least by sitting at your homes, people developed models like this. Okay, people develop model like this, and therefore it is useful. Wherever you go, even this SIR model, like how many are infected, how many are susceptible, how many have recovered, susceptible, infected, recovered. All these models can be framed using coupled differential. So you can see like the dynamics of hen. The population of hen depends on the virus. The population of virus also depends on the hen. If one hen is super immune, then the virus population will decrease, isn't it? So it will not spread. So therefore, one will act as a barrier. So therefore, he captured the dynamics of both hen and virus. I mean to say, like you can say lion and deer also. Okay. And this is a couple differential equation. So how will you solve it? That is the question. How can you solve it? So you can solve using the same RK4 method we had discussed in the beginning of the class. You can see that it has 8, we did with 8 unknowns, K1, S1, L1, P1, K2, S2, L2, P2. Instead of that, they have KX1, KY1, KX2, KY2, KX3, KY3, KX4, KY4. Okay. And it's the same what you have done in this course, like in this class today. It's almost the same, they have coded it. Okay. And then you just compute Xi's and Yi's same way as RK4. Okay. And we plot it. And we plot it. Okay. It's known as the predator prey model. Predator prey model. Predator will eat the prey. Okay. So predator may be lion, X may be lion, Y may be deer. Okay. So how it looks like? To understand the population of predator and prey with respect to time, we have to plot as a time series according to the population. When we plot using time series for a particular parameter, you get something like this. Okay, you get some solutions like this. Now, it is something interesting solution, because it is not a solution where it is just like a straight line. It's saying that population is not constant. Population is increasing, population is decreasing. Okay. Why population will increase? When population increases, think intuitively, this mathematical model actually captures the intuition. Okay. Very, very nice argument is there. If the population of deer increases, what will happen? Then they will come in contact with lion easily. Then the lion will eat the deer. Okay, lion will eat the deer. Okay, so population of deer increased. Then when the lion started eating the deer, okay, then the deer population will decrease. Now it decreased. So when the lion ate the deers, okay, they got fat. Okay, they got fat, and yeah. So after some time, lion population will also decrease. Okay. So you can see this up and down thing, like oscillations here. And if you plot them together, predator versus prey, number of predator versus the number of prey. you get a closed curve. Okay, so this looks like an egg, fine, but it is periodic. It is periodic. Like you can see that if it looks like this, these points will again come with respect to time. It will lie on that circle. Okay. Now let us come to something very nice. I think I will give you one example of coupled differential equations, which we'll see. Maybe I'll show you just here. So you can see this Lorentz system, okay? So this is also a coupled differential equation system, like dx by dt, dy by dt, dz by dt. Okay, x, y, and z are all coupled with each other. And most importantly, it was developed by Lorentz in 1963 to model this atmospheric convection system. Okay, so you can see how the dynamics looks like. The dynamics looks like this. If we have a maybe yeah, I just want to show you one small video. So it is just like this. Like you can see these are the trajectories of these differential equations, and it is just making a butterfly shape. Okay, and it is unpredictable also. Okay, you cannot predict actually where this lobe goes. Okay, so it started from here, then it went to the next lobe, then next lobe. Okay, how many time it stayed with one lobe, how much time it stays with the another lobe, it is highly complicated. Okay, so yeah, this is one visualization actually. You can see this.
may be familiar with position time or velocity. But what radiating plot represents every possible state, every possible thing you do in one order. Except that's what you can and physical because if the one is people just go down the slope. By universe higher, lower and left are even. And it doesn't really matter what the conditions are, we know that the final state will be available after pains for you again. From the graph, it's like this is the attractive, the order like one fixed point. So it's probably a fixed point. Yeah, and then that would be what's back and forth with anyway. And basically, the bottom spin in the opposite direction and it goes back and forth. The closed loop tells us that the motion is periodic and regular. Anytime you see things like this in base space, whether this is regularly repeats, different size. The other important thing to know is that the curves never cross in bases. That's because each point identifies the statements stating something one from the other. So once you define the initial state, the entire feature is determined. Now, it's not going to be well understood using physics, but so where opposites are not submitted to different places. So the really can't put the we will not get from coffee and when the facts of the result, the risk was that they move around following over equation for a while and diverge. And pretty soon we see the values, two values in totally different weapon. The rest is first off. This difference down the fact that the term into three decimal places where the computer says. So when you enter those initial digits, the inference of less than 1 part of that being computed better than just a short line of a computer. However, this simple lines and greater than simple lines and more, just and variables represent one model of convection. Things like the atmosphere, heated at the bottom and cooled at the top. But again, you got the same thing with behavior and changes that are hanging dead. The results average dramatically. The random system is way with the compound has sensitive dependence on any conditions, which is the hallmark of chaos. And since the random we're doing 3 variables, we can plot the base space of the system in 3 dimensions. We can make any points that are using for the falls. Does not point food or affects the track or we that's what I'm saying. A certain system will never reason that state. Here I actually started with this closely spaced states. Now for being together, they have completely different patterns. This is the system. Now, I should point out that there is nothing written at all about the system of equations. It's just like so if you could exactly the same equations, you would get exactly the same result. The problem is this system is the counter. So any difference in conditions, no matter how clean, will be amplified to a totally different final state. It seems like a paradox, but this is going to go deterministic and unpredictable. Because in practice, you would never know it's perfect accuracy. I'm talking infinite decimal points. But the result suggests why you think it's so hard to forecast the weather that we in advance. In fact, instead of combining mean data with long-range forecast, prediction is less accurate than if you just look at the historical averages for that day. And you don't see how this depending on some conditions and in seven of the things. Now, how being the second rule, we have to the double minimum, just so two simple things is reality. Here, double minimums have been released from the same conditions. As a release, the double minimum in the same way as once. It's emotion, but we're every unpredictable. Given the thing that the chaos requires a lot of energy or but this system of the five disconnected propelling magnets in each of their lines is chaotic too. At first glance, the system seems perfectly predictable, but if you want to look more closely, you'll notice some straight that's there suddenly the other way. Even the solar system is not predictable. If you play for 100 billion years in the future, this behavior doesn't being count. You're not seeing for the years. That means within the same or 15 million years, some of the hormones may have applied or may be flung out of the specific. It's unpredictable by even process. So we're not all we predict the future. Not very well at all, these systems. Even further into the future, we try to predict environmental economics. Certain predictions aren't better than guesses. The same is true when looking at the past together systems and trying to identify the problem. I think that how about law in the further we look into the future or the past. Chaos means I really what we know about the future of systems and what we can say about their but there is a silver lining. Let's look again at the base of reference to awakening. If we start with a whole bunch of different information and models at the moment, it's really is that. But signal reports more once you know. The object presenting was a bit of about it is the entire largely information pieces of the law was taken on an or the all they got in the process. If it is, see on that this particular factor is called the red factor.
Yeah, so I think like you somehow understood this. Okay, so what is happening here and why they are so complex to solve? Yes, so how the things you are learning, like the ODE methods you are learning, can be applied here, like not manually, at least using Python codes. Okay. Fine. So yeah, this was the plan. Yes. So therefore, yeah, this is just one ODE method I have showed you, like 2D, like 2D Lotka-Volterra. Then you saw this 3D Lorentz system, which is chaotic and highly unpredictable. You can see how it moves in phase space, like a butterfly effect. Okay. So you can see that solving just ordinary differential equation is okay, but it's already been done. So what is new in this era is to understand highly complex systems which are just formed by just coupling the two ODE equations, okay, or three ODE equations. So they are coupled system of differential equations. So coupled system of differential equations are not that simple, but you can see that a variant of RK4 method can be applied to understand them. Okay. So I think we can start after the break. Okay. So, yeah, we can start with the PD.